for today's Low Physics webinar. My name is Alejandro and I'm going to be your host. Today we are presenting Polarized Images of Black Holes by Andrew Chael. Andrew got his bachelor in arts in physics with a secondary concentration in medieval studies from Carleton College in 2013. Then he went to Harvard to get his PhD in physics. He got it in 2019. And then he was a NASA Hubble Fellow or an Einstein Fellow that he took to PCTS, the Princeton Center for Theoretical Science, since 2022 to 2025. Sorry, actually, after he finished his PhD, went to NASA Hubble, and then he was an associate researcher at Princeton from 2022 to 2025. And he, this semester, joined the Niels Bohr International Academy at the University of Copenhagen as faculty, where he is now leading the efforts in many, many topics where he's an expert on, including black holes, accretion, jets, MHD, and computational imaging. Andrew is also a member of the Event Horizon Telescope collaboration. So we're very happy to have you here. And today we'll hear about polarization signatures of these images. So for everyone, remember that you can ask questions over email through our YouTube channel, and then the questions will be read at the end of the talk. So without further ado, Andrew, let's take it. Let's please take it away. Thank you for joining us.
Great. Thank you so much to Alejandro and all the organizers for inviting me. I'm really excited to tell you a little bit more about my work in understanding polarized black hole images. Yeah, as Alejandro said, I will be talking all about polarized images of black holes. Here are the two polarized images of black holes we have so far of the galactic center Sagittarius star and M87. And hopefully in this talk, I'll give you a whirlwind tour of how we get these images and hopefully convince you that they're important and interesting and we can learn a lot from them about both physics and gravity potentially. Okay, come on. Great. So just setting the stage a bit, if we look up into the night sky, we see, of course, if you're in a good observing site like this, you see the spread of the Milky Way galaxy, and zooming into the core of that galaxy, into our galactic center. Over the past 20 plus years, astronomers have tracked in infrared light the orbits of stars moving around a central dark mass. And from these stellar orbits, groups in both the US and Europe were able to determine that at the center of our galaxy, there's a dark mass of more than 4 million times the mass of our sun, which doesn't shine like our sun does. And this sort of is the most concrete evidence that one of the pieces of most concrete evidence we have for the sort of existence of a supermassive black hole at the center of our galaxy, and it won the Nobel Prize in Physics in 2020. But zooming out sort of beyond our own galaxy, we now think that supermassive black holes live in the core of basically every galaxy in the universe. And they're both very interesting objects in their own right, but then also extremely important, we think, in sort of regulating the interaction of galaxies and their larger environment. So black holes can eat gas from their host galaxies and then expel gas and momentum out to large distances. And one of the most spectacular ways that they feed back onto their larger scales is through these extragalactic jets. These have been observed for over 100 years now, and they exist in many galaxies. Here's a sample of them spread out, and where we're seeing the light from galaxies in optical, and then the light from these jets that emerge from the central supermassive black holes in the radio. For example, spectacularly here in the galaxy Hercules A. And these black supermassive black holes are, many, many, many times smaller than their host galaxies, but they still are able to shoot out tremendous amounts of material and energy and momentum in these narrow jets at nearly the speed of light to distances even outside of the host galaxy itself. And so this, we think, is a very important part of how galaxies and black holes talk to each other. So one of the most studied examples of these extragalactic jets is that in the M87 galaxy. It was actually the first one discovered over 100 years ago. You can see it here in an optical image from the Hubble Space Telescope. And over the last 50 plus years, by looking in radio light at progressively higher and higher resolution using very long baseline interferometry, we've been able to track this jet down from scales of thousands of light years down to the core of the galaxy itself to sort of this image here on the right, which when I joined the field more than 10 years ago now was the highest resolution image we had of the M87 jet, looking at scales that are much smaller than a single light year. And so, yeah, when I joined this field, the question was sort of, can we take the next step and look even further down closer to the core of this jet and look at what jet launching looks like on the scales of the event horizon of the black hole itself? And the key innovation that has allowed us to do that in the time that I've been working on these problems is the Event Horizon Telescope, which is a network of telescopes operating around the world at 1.3 millimeter wavelength, using very long baseline interferometry to essentially synthesize the resolution of a single Earth-sized telescope. So this is the highest frequency that very long baseline interferometry has ever been done. And by sort of just using the relationship that the resolution of your telescope increases with both the frequency of light that you're observing at and also the size of the telescope that you use at 1.3 millimeter wavelength, and with a telescope around the size of the Earth, we're obtaining resolutions on the order of 20 microarc seconds, which is just exactly what we need to begin to resolve the nearest supermassive black holes. And so we put out images of both the one in our galactic center, Sagittarius star, which is on my first slide, and also M87 here at the core of this relativistic jet. And we're not only looking at these images in total intensity light, but also in polarization, which in this image is indicated by these curving lines on top of this sort of image of the central supermassive black hole, and will be the focus of the rest of the talk. But basically, the key question that I work on these days is trying to understand, can these images, particularly of M87, which is looking at the very heart of this extragalactic jet, begin to tell us about the processes of how these jets are launched and how magnetic fields and black holes work together to produce these spectacular outflows of energy. So we've learned a lot from black hole images. In particular, just looking at the two that we have so far, both in M87 and in Sagittarius star, despite the fact that these black holes are thousands of times different in their mass, so Sagittarius star is 1,000 times less massive than M87, the images look about the same when you scale them appropriately. And that's telling us something about sort of the scale invariance of the accretion physics, how these black holes are eating matter and launching material. We've also seen that there's images that are well described by our best theories of both astrophysics and general relativity. So we think that we understand how the gas is heated up and produces this characteristic ring-like emission. And we think that the central brightness depression is being driven by gravitational redshift and lensing. And we also know from the polarization, again, we'll also in more detail later on, that these black holes are surrounded by strong and coherent magnetic fields, which are very important in determining how they interact with their environment. But despite all this progress, there's still a lot of mysteries, and those would sort of power what I work on. In particular, trying to understand what powers the extragalactic jet in M87. We don't actually know precisely how this spectacular structure is energized. It could be powered from the spin of the accretion disk, so the rotation of the large-scale accretion disk, or potentially, and most interestingly for me at least, that it could actually be tapping the spin of the black hole itself to power these magnetic fields and matter acceleration out to large distances. I also work on problems like trying to understand how particles are accelerated that sort of produce the light that we observe, and how we can most precisely measure the black hole spin and test general relativity with these images. But the focus of my talk mostly today will be on understanding these jet power questions. Yeah, so to set the stage, why is polarization interesting for us? So polarization is important because the synchrotron radiation that we observe is generated by electrons gyrating around magnetic field lines, like in this very nice little animation. And these gyrating electrons produce their polarization direction, sort of the direction that their electromagnetic field is oscillating in, perpendicular to the direction of the magnetic field that they're oscillating around. So this gives us an immediate way to look at how magnetic field lines are arranged around these objects, not just black holes, but other objects that are all of astrophysics. But it doesn't tell the whole story. This direction can actually change as it goes from the electron where it's emitted to us. And that's how that polarization direction changes is very sensitively dependent on both the strong gravity of the black hole itself, where it sits in its gravitational potential, and also the local magnetic field and plasma. So polarization is immediately telling us a lot of things, both about the magnetic field, the plasma, and space-time, which is the good news. It's very sensitive to all of these interesting things we want to learn about, but it's also difficult to disentangle all of these effects and try to piece back from the polarization what we can learn about all of these interesting physical properties. And so, yeah, just to set the stage for the rest of the talk, we'll be showing a lot of polarization images. We show polarization images in sort of two different ways. On the right here is this sort of wind plot approach, where we show the black hole emission in red, and we have sort of the polarization direction painted on in these sort of wind-like lines. And on the left here is a sort of more tick plot approach where we have the black hole emission in grayscale, and the polarization direction is indicated with these ticks, which are colored by how polarized it is. And so I'll probably mostly be using this form on the left, but I just want to sort of orient people around both types of plots. Okay, so in the rest of the talk, I'm going to sort of zoom through a lot of topics related to black hole polarization. I'm going to spend a little bit of time at the beginning talking about how we make these polarized images in the first place from EHT data. Then I'm going to talk about how we learn what we've learned about from these images from comparing the polarized images of black holes we observed to simulations. I'll talk a little bit more about sort of physically how we can extract some information about how energy flows around black holes from polarized images and how that might have implications for jet launching. And then hopefully at the end, we'll have some time to talk a little bit about what we might do next with future observations. So yeah, first jumping into how we obtain these polarized images of black holes. So again, the EHT is a network of radio telescopes all around the world operating at 1.3 millimeter wavelength. Here's just a collection of very nice pictures of all of the telescopes in our array. And but the EHT is not just a collection of telescopes, it's also a collection of people made up of people from institutes all over the world working together to sort of both get these telescopes to work together to conduct these groundbreaking observations, but also then to analyze and interpret the data, which is a very difficult task, as you'll probably see in some of these later slides. So especially in this section, but throughout the talk, a lot of the results I'm presenting today would not have been possible without this global collaboration of people. So yeah, as I said at the beginning, the EHT is working on this principle of very long baseline interferometry. And the basic idea of VLBI is that every baseline or pair of telescopes, every separation between two different telescopes on the Earth, provides us a measurement essentially of one component of the Fourier transform of the image. So basically every baseline separation between two telescopes is measuring a single spatial frequency, which you can think of as living in this plane of north-south spatial frequencies and east-west spatial frequencies. So it's giving us one plane wave in the Fourier decomposition of the image. If we had sort of infinite telescopes covering the entire Earth, we would measure all these components, and we'd be able to simply invert the Fourier transform and obtain an image. But because we only have certain telescopes and therefore only certain spacings between them, we only fill in a small fraction of this larger plane. This central image here shows the number of points of data we accumulate. And you can see it's a very sparse set of points compared to this entire plane, which ideally we would like to have measurements everywhere. And it becomes an immediate problem to sort of take this sparse set of measurements and convert it back into an image that we can then interpret. Because we're not measuring the image itself directly, we only have this sparse set of measurements of its Fourier transform. But the problem doesn't actually end there. That's only half of it. The second issue with EHT data that makes imaging challenging is that we have corrupting effects in our telescopes that add systematic uncertainty and biases to our observations. So particularly in polarization, we have several different effects. One of these is that the atmosphere is turbulent and sort of delays the propagation of the signal from the sky to each individual telescope differently. And we don't know how that is happening a priori, and so we have to solve for that. Another is that the sensitivity of our telescopes is calibrated quite well, but maybe not entirely perfectly all the time. And so we might not exactly know how strong the signal is in one telescope versus the other, which is very important for trying to assemble these Fourier components and create an image. And the third is that we actually have leakage between the two different components of polarization, either X and Y or right and left circular polarization. These actually leak into each other in the electronic signal chains of our telescopes, and that has to be accounted for as well later on. So with these sparse measurements and these corrupted measurements, we have to turn them into an image. And we do this through a set of reconstruction algorithms, which here are represented by this black box. And one of, I think, the strengths of the EHT collaboration approach over the years has been to really test and compare against each other several different types of reconstruction algorithms based on different fundamental principles and authored by different groups of people. And we've found in most cases that these algorithms, after a lot of work and testing and calibration, are able to arrive at the same results on our data, and it's really only in those cases where we have strong confidence that what we're reconstructing in terms of our image is actually representative of reality. And I think it's this comparison approach that has really served us well in giving us high confidence that the images that we're reconstructing from our sparse and corrupted data are accurate representations of the black holes on the sky. So I've been part of this effort myself in terms of authoring one of these packages that is used to convert ESG data into images. And this is the ESG imaging software library. I won't get into too much detail of it, but it was one of the early things I did as a grad student to sort of create this this library, and it's been used in many ESG publications. And I think hopefully it's been useful sort of beyond the EHT as well in other areas, and as a toolkit also for developing new tools for things like dynamical imaging and multi-frequency modeling as well. Okay, but back to polarization, we use this sort of set of different imaging techniques. In this case, for the first images of M87 that we did several years ago, we used 5 different imaging methods spanning a whole range of approaches, and we came up with these 5 different independent reconstructions of the of M87 in polarization. And we see that all of them, while they have slight differences, which might depend on the different choices the methods make, feature the same broad trends, which are the ones that we're confident in and we can physically interpret. So in particular, all these methods show similar ring-like structure and total intensity and grayscale. They show the polarization in these tick marks is predominantly helical. It has this characteristic twisting pattern around the ring, and it's relatively weak. So if you look at the sort of level of fractional polarization, how much polarized light there is compared to unpolarized light, it's about 10%, which isn't that high, especially for synchrotron radiation, which we think should intrinsically be quite highly polarized. That was the first images from 2017. We've now taken the next step, and last year released a paper with 2 new epochs, both from 2018 and 2021 in linear polarization. And while they show a lot of similar trends, in particular, the stability of this emission ring has now confirmed over 4,000 gravitational timescales. We actually see changes in polarization, which are a little difficult to understand in some of our theoretical models, which I'll be talking about next. And in particular, this polarization structure seems to be shifting and is actually even less polarized in some of the later years. So understanding this evolution and tracking this evolution even further into the future with more observations. We have observations beyond 2021, so in 2024, 2025, and we're conducting a movie campaign of observations now over several months. We're actually observing M87 week to week. By extending this time baseline even further into the future, hopefully we'll learn even more about sort of the average polarization statistics of M87 and get a better picture of what it looks like over time. Okay, so that was just a brief introduction to how we obtain these polarized images and what they look like. In particular, I want to emphasize again that they have this characteristic helical pattern and low level of fractional polarization. And in the rest of the talk, I'm going to switch gears and speak more with my theorist hat on and talk about what we can learn from these images and how we compare them to simulations and theoretical models. So the first approach that we have often taken in the EHT, which I think has been a very useful one, is to interpret black hole images with simulations. And in particular, we use these large libraries of general relativistic magnetohydrodynamic, or GRMHD simulations. And that's a long acronym, but basically it just means that they live in a black hole spacetime. So the general relativistic, they're hydrodynamic, so they're tracking the motion of fluid, and they're magnetohydrodynamic, so they are tracking the coupled evolution of the fluid or plasma and magnetic field. And this is just an image, a slice through a simulation, looking edge on the black hole. So we're looking through the accretion disk. The accretion disk is this big, thick structure here. We're seeing the material fall in onto the black hole and then be expelled along poles in this beginnings of this relativistic jet. We then take these simulations and run them through radio transfer codes. So these track the light rays that propagate through these simulations and solve for the polarized radiation that is accumulated along light rays, including the effects of Faraday rotation, as well as the strong gravitational light bending. And we produce movies like this, which show the black hole and material rolling, rotating around it, as well as the polarization here in these dancing tick marks. So, like I said, we assemble not just 1 or 2 of these simulations, but large libraries of them, which span many different parameters of things that we want to understand more about, things like the black hole spin, the angle that we're observing it relative to the black hole spin axis, the physical parameters that set the electron temperature. That's a big area that I want to be able to talk too much about today, but it is something I think a lot about because we don't actually understand all that much about what sets the physical temperature of the emitting electrons. And we produce a large sample of different images, particularly here covering different black hole spins and different magnetic field configurations here on the left. And then on the right are the same images blurred out to the sort of resolution that the EHT sees. So the left is the sort of native resolution. And even with our Earth-sized telescope, we're only able to get a blurry image of these black holes. And so we actually observe things that look more like this on the right. So one of the key parameters that we want to understand more about is how the magnetic field works around these black holes. And this is very important because we think the magnetic field is what's responsible for launching the jet in M87 out to large distances. And in these simulations, we have observed sort of two different types of magnetic field configurations that correspond to what we call sane and mad disks. In the sane approach, magnetic fields are sort of weak and turbulent, and they get sheared around with the disk and basically just follow what the accretion disk tells them to do or what the plasma is telling them to do. Whereas in the MAD approach, in the MAD paradigm or magnetically arrested disk case, the fields are much stronger and they build up coherently into these strong coherent structures. And these fields build up on the black hole horizon and are able to actually push back against the infalling gas. They're dynamically important. And this MAD picture is really appealing for a lot of reasons. And one of them is that these magnetically arrested disks should sort of naturally launch more powerful jets. So we think when jets are powered by black hole spin, that the power in the jet is proportional to the magnetic flux squared, as well as the spin squared. And so if you can pile on more magnetic flux onto the black hole, that would explain how you could get some of these stronger jets. But this telling the difference between these two different paradigms isn't actually something that people were able to do directly looking at emission from the black hole itself before the EHT came along. And also when the EHT first released its images without any polarization information, we were also not able to say anything about this mad versus sane or magnetized versus relatively unmagnetized dichotomy. So I think one of the great successes of the EHT and the sort of theoretical simulations behind it is that the images that we observe actually are very consistent with GRMHD simulations. Like this didn't have to happen. We didn't, have to be in this case where the simulations that we had even before the EHT existed looked a lot like what we observed. Here's just an example from back in 2019 when we released our first images showing that sort of the blurred GRMHD looks quite a bit like what is actually seen in M87. But sort of the downside of this striking agreement is that it actually turned out that a lot of different simulations with a lot of different physics, whether that's black hole spin or different electron temperature models, could be made to look like our total intensity images if we were just tweaking the free parameters that we have. So we can scale things like the mass and the total flux density. This basically tells us that our overall paradigm is very successful at explaining what the black hole images looked like in total intensity, but we weren't able to say much more about sort of the details and the physical parameters within that paradigm before we had polarization. But polarization immediately changes that picture, and you can just see that by looking at this panel of images on the right. Here again, the grayscale underneath these polarized images from simulations is showing the total intensity. And you can see that all of these images show, despite quite different underlying physical parameters, showed basically a similar ring-like structure caused by the gas falling into the black hole, and the gravitational redshift and strong lensing. But if you look in polarization on the tick marks, all these different images look quite different. They feature helical and toroidal and radial structures. They're strongly obliquely polarized. And so just immediately by looking at these images, we're able to hope that with polarization, we can start to rule out more of our models and learn more about what the underlying astrophysical parameters, and particularly magnetic field, how that's behaving near the black hole. And this turned out to be correct, this sort of intuition, by carefully scoring our observations against different GRMHD models in different ways. We were able to actually constrain which models were favored much more strongly using polarization than we were with total intensity. And so in particular, we found that basically all of the different approaches we took at comparing simulations to the real images from the EHT, all of them favored these magnetically arrested or mad disks much more over the weak field simulations, which you can just sort of see here in the sort of simplest scoring comparison, which is just looking at how many images pass all of our different tests. Basically, all the passing images are from magnetically arrested side of the plot. And this allows us to do things like constrain the accretion rate of M87, how fast it's eating matter, as well as the magnetic field strength on the horizon. And it gives us, again, more hope that, we understand how these jets are being launched, because we have we're probing directly with the EHT images strong magnetic fields on the event horizon, which may be responsible for extracting the spin energy of the black hole and producing these jets. Again, this sort of picture, I think, is complicated by our new polarization measurements. And so we still haven't done that full analysis of how these new measurements from later years of observation might change or shift around this picture. But I and many other people in the collaboration are working on that right now. So I think you should stay tuned, and hopefully we'll have some results there relatively soon. Yeah, I just want to give a brief aside that J star, while I'm not talking about it much in this talk, in our galactic center, it looks quite similar in polarization. Despite not featuring an extragalactic jet on large scales, it seems like it also has very strong magnetic fields around it, and is also described by these magnetically arrested simulations. It has a slightly higher polarization fraction than M87, so it seems to be more polarized. And it has a similar sort of sense of polarization spiral as we observe in M87. And as we'll talk about in the next section, that sort of sense of polarization spiral is actually telling us something potentially about how energy flows in the system. And so it seems like for J star and for M87, despite, again, this difference in over 1,000 in a factor of 1,000 in their black hole mass, the sort of underlying conditions of the accretion flow around them are actually quite similar. Okay, that was just how we initially approached the problem of interpreting these images with simulations, and what we learned from that, which is basically that the black holes are highly magnetized. And now I'm going to talk a little bit more, diving into the physics about what these polarized images tell us about energy flow, and potentially about how the jets are launched in M87. So again, just to set the stage, M87, this EHT image we've been focused on, that I spend much of my life thinking about, is just one piece of this larger structure, this extragalactic jet, which extends out from the sort of solar system scales that we're looking at here, solar system size scales we're looking at here in the EHT image, out to thousands of light years, or even past the host galaxy itself. And we think these jets are powered by black hole spin energy. This has been sort of the predominant explanation ever since Blandford-Znajek put it out there in the 70s. But the system actually is something we ever observed directly, and there are other models. And so it's something we'd really like to be able to probe directly on these event horizon scales. Is the energy in the jet being extracted from the black hole itself? And from the simulation perspective, I think we have a lot of good reason to think that is indeed the case. We've known for a long time that jets from simulations are indeed powered by the black hole spin, because we can just go inside the simulation and see where the jet power is coming from. We have images that from the simulations, which look a lot like the images of the base of the jet in M87 that we obtain in reality. These are just some that I did several years ago now. There are much more modern ones that look even better than these, but I think these also convey the broad point that we are able to produce images of jets that have both the same total power and the same sort of wide opening angle and observed core shift that are actually observed in reality. But this is sort of a circumstantial comparison in some ways. Like, we see jets in simulations that we know are powered by spin, and we see jets in reality which look a lot like those jets in simulations. But we'd really like to have sort of a more physical, direct comparison of some firm observable that would allow us to more directly test this connection. Oh, this slide is just basically showing that the jets from simulations do indeed obey the prediction from Blandford-Znajek about where they're getting their power. They can produce more outflowing energy than goes into them from extracting the black hole spin energy. Okay, so the key metric that we, I think, are arriving at in terms of understanding, linking the jet launching physics to observations is this, basically the sense of the spiral of polarization vectors around the black hole image. And so we noted earlier that the polarization vectors around the black hole are have this characteristic spiral structure. We characterize that spiral in terms of this beta 2 coefficient introduced by Daniel Palumbo in 2020, which is basically just the second angular mode, m=2 mode of the polarization around the ring. And so you can, this is written down like this, as like a Fourier transform around the ring. And you can interpret different types of this beta-2, or different phases, in particular it's beta-2. This beta-2 is a complex number, and so it has amplitude and phase, and its phase is the most important part. And different phases of beta-2 tell us basically how the polarization spiral is oriented, whether it's radial or azimuthal, or whether it's right-handed or left-handed. And in particular, when we're looking at the spirals, which are either right-handed as in this case, or left-handed as in this case, considering the spin of the black hole to be into the page here, we can characterize those as having the phase of beta-2 either being less than 0 for the right-handed spiral or greater than 0 for the left-handed spiral. And sort of stepping back for a second, if we sort of ignore all the details of all the complicated physics between the observer and the source of the curved space-time and rotation through Faraday rotation through the plasma, we can sort of connect this directly to the pitch angle of the magnetic field. So the polarization is emitted perpendicular to the magnetic field. And so just backing that out, observing a spiral like this, the right-handed polarization spiral, should tell us that the field, the toroidal field, is negative relative to the radial field, and vice versa for the case here in this panel. Again, with the coordinate axis being into the plane of the sky here. So basically, if we can throw out all the complicating effects, which in reality we think are quite important, and we're able to just simplify it down to this picture, measuring the observed sign of beta-2 tells us immediately how the azimuthal part of the magnetic field relates to the radial part. And we're in this regime, at least for the first images of M87, where we are observing a negative angle of beta-2, and that corresponds to the toroidal part of the field being negative relative to the radial part. And sort of the key insight that we had a few years ago is that this actually is directly probing how energy flows around the black hole, simply because in GRMHD, or in strongly magnetized plasmas, basically when you write down for an axisymmetric system what the direction of outward energy flux is, whether energy is flowing in or out, magnetic energy, it turns out to be directly related to this product of the radial and phi components of the magnetic field times the angular velocity of the black hole, which we think is positive in this convention. So basically, if Br and B phi are negative with respect to each other, if we have them wound up as in this configuration, we think that we're observing energy flowing outward. If we had observed the opposite, that would have either told us that we're observing energy flowing inward, or that we had more work to do in trying to calibrate and understand our observations. But this, again, is a very simple picture, and it's a cartoon. And so the question immediately becomes, do we observe this same sort of trend in beta-2 in simulations, where we can actually go in and measure what the direction of the energy flow is? And it turned out that, in fact, we could. So these histograms here on the right are showing sort of the distribution of the angle of beta-2 extracted from simulation images for a range of black hole spins. And with the coordinates set up like we think they are in M87. And basically, in all these cases, we observe negative sign of this phase. And so that we think, because we can actually go into the simulations and see that all of these simulations feature energy outflow on these scales, that the fact that all these angle beta-2s are indeed clustered left of the 0 line tells us that this is actually a good probe of that direction of energy flow, or alternatively, the direction, the sense of the windup of the magnetic field, which is essentially the same thing. And in fact, based on our original measurement from 2017, M87's horizon field polarization is consistent with the fact that we should have outflowing electromagnetic energy on those scales. So very close to the black hole, we think we're observing electromagnetic energy flowing outward. We also see here that the angle of beta-2 in the simulation has a strong dependence on the black hole spin. So for example, as we go up in black hole spin, as we make the black hole spin more rapidly, the angle of beta-2 goes from minus 180 degrees closer and closer to 0. And this is also something which is relatively easy to understand in the simple cartoon picture. So, and that becomes, when it's spin dependence of images on the spin dependence of polarized images is essentially related to how fast magnetic fields are winding up. So the black hole spin is essentially winding up these initially radial magnetic fields, always in the same sense, so that B phi is negative relative to BR. But basically how fast that B phi component is dominating over the BR component depends on the spin. For a low spin black hole, the fields wind up, but they wind up more slowly. Whereas in a high spinning black hole, the fields are winding up very quickly. And so you very quickly get magnetic fields, which are basically entirely in the toroidal direction. And this manifests directly into the polarization in simulated images. And in this case, these are average images from GRMHD simulations, which include all the time variable turbulence and all of the 3D effects, which are ignored in the simple cartoon picture. But you still see in the average that they basically show the expected behavior, where a low spin black hole has a helix of polarization, which is more toroidal. Again, the polarization is rotated 90 degrees relative to the field. And so the more radial fields in the low spinning case translate to more toroidal polarization. And for the high spinning case, we have very radial polarization vectors indicating that the underlying field is very wound up. And this increased field winding with spin is increasing the jet power, and it's also making the polarization pattern more radial, as I said. And we can look at this trend again in the arg beta 2 language, the phase of this beta 2 statistic, and we can see that we have this characteristic trend of beta 2 towards 0, indicating more radial polarization, both for prograde and retrograde black holes. So exactly how the pattern progresses is different in the prograde and retrograde case. And this gives us hope that we have in beta 2 a way of measuring black hole spin. It's a measurement I think we're not ready to do yet, because we still have to understand all the complicating effects, like all the plasma effects and initial conditions, which might shift around this overall relationship. But I think the overall sense of this relationship from more negative arg beta 2 up toward 0 as you increase spin is something which is robust across models. And so now the task is to sort of understand the uncertainty in any of these individual measurements and calibrate it. Yeah, the last thing I'll say in this section is that another thing that's very important is Faraday rotation through the plasma. So Faraday rotation is basically the fact that as we progress the polarization through the magnetized plasma, its direction is rotating. And this is both a source of uncertainty for us, basically, because it shifts around the direction of polarization from our initial prediction and makes measuring things like connecting an individual spin on an individual beta 2 point here to an individual spin more complicated, because the astrophysics of this Faraday rotation is getting in the way. But it also, we think, is very responsible for one of the key features of our polarized images, which is that we see them to be relatively low polarization. So that's illustrated here in these two different models, which are the same snapshot of simulation, one without any Faraday rotation and one with Faraday rotation. And you can see that sort of at the infinite resolution scale, we had perfect glasses, and we could see these images entirely clearly. We would see very high polarization everywhere in the image, but with Faraday rotation, that polarization is a lot more scrambled, because each of these different polarization vectors is propagating through different magnetic fields and different plasma pockets as it's sort of going from source to us, and that causes the polarizations to be scrambled. When we then blur these images and view them at the resolution scale that the EHT sees, we're only just able to make out the black hole, that sort of scrambling on the left-hand side basically averages out the high polarization, and we get a much lower polarization average on the scales that we're measuring with the EHT. And so this Faraday rotation, we think, is very important for determining how we can obtain these depolarized images from synchrotron radiation, which is intrinsically high polarization. And it's also allowing us, giving us a direct probe of the electron temperature, because basically this Faraday rotation is much more efficient in colder electrons than it is in hotter ones. And this is actually something else I work on these days, and it's I think a big challenge to our theoretical models. Basically, the EHT analyses that we've done seem to prefer much colder electrons. So in particular, having ions in the accretion disk that are about 100 times hotter than the electrons, or electrons that are 100 times colder than the ions. in order to produce sufficient Faraday rotation to depolarize the image. But when we attempt to do these simulations more self-consistently, throwing in more physics and actually evolve the electron temperature against the ion temperature and not just assign it after the fact, we actually have found that most of our models don't predict ion temperatures, which are electron temperatures, which are that cold. We usually obtain things which are only a few times colder than the ions, electrons that are only a few times colder than the ions. And so I think this is an active area of work. And as you can see here, those produce polarization fractions across all the range of black hole spin, which are much higher than what we observed. Here's the polarization from some of these simulations, which are attempting to do the electron ion physics more self-consistently. And here is the observed band. So I think this is an area where we still have a lot of work to do and we still don't understand the full picture, but basically it seems like we prefer very cold electrons around these sources, both Sagittarius and M87, though M87 seems to be colder. And I think it's an open question of whether there's some aspect of plasma physics that we can introduce into these more self-consistent simulations, which would help us obtain those colder electrons, or maybe there's something wrong with some of our bigger picture assumptions that we need to revisit. Okay, so I guess in the last 5 minutes, I will step through briefly some of the next steps we have for taking everything I've talked about now to the next level and trying to determine more about the black hole spin and jet power source with polarization. And sort of the conceptual framework here is that basically, so far with the AHT, we're only looking at things on sort of one scale. So we're basically looking at this ring of emission around the black hole, and we're measuring the polarized properties of basically one radius. But to make progress, I think we're going to do that in two different ways, and both of them relate to measuring polarization on a wider range of scales, both by zooming out, basically by looking at how the black hole is situated in this larger scale jet, and imaging the connection between the black hole itself and the base of the jet in polarization and in high dynamic range, because this jet is much dimmer than the black hole that ring that we're already observing. And then by zooming in and actually trying to look at the evolution of these polarization vectors, or which are connected to the evolution of magnetic field lines as we get closer to the horizon and higher resolution. And both of these goals, I think, are very adapted to sort of two directions the community is taking over the next decades to extend the work that the EHT has already done. One of them is in this sort of extended and next generation EHT project, which is to build out the array of telescopes on the ground that we observe these black holes with, basically to make our images more accurate and get higher and higher sensitivity to this low brightness emission, like we think is in the base of this jet. Because basically, as you add more sites to your ground array, you're able to obtain images which are sensitive to dimmer and dimmer features. And the other is this Black Hole Explorer mission project that I'm a part of that is aiming to put a element of the LBI array into space. So basically, by increasing the distance between the telescope in space and all the telescopes on the ground, we'd be able to increase our resolution by a factor of 3 and go from images like this here, where we have a very blurry image of the black hole to much more sharp ones like here. And one of the main driving features of this effort is to resolve the extreme gravitational lensing of that is concentrated in this narrow photon ring. Alejandro, who invited me, is an expert in this, and I won't talk about it much, but I'll talk a little bit about how Black Hole Explorer, I think, is also interesting for polarization. So yeah, first, again, zooming out into the extended jet, basically, the picture here is that by tracking the evolution of polarization over larger scales out to larger distances, we're actually able to begin to probe energy flow, not just from the black hole, but out into the jet that we observe already with different VLBI experiments. And I've been working a lot with a student at Princeton, Zach Ellis, who has developed a lot of the ideas and tools that we have needed to go beyond sort of the EHT skills and into the extended jet. And what he's found is that he sees a strong signature of the polarization of these jets at the light cylinder radius, so basically where the fields are co-rotating at the speed of light. And you can sort of track out the evolution of polarization not just at one radius like we're measuring with the ASG, but by going out to thousands of hundreds of thousands of gravitational radii, you're actually able to see this characteristic swing upward in polarization, and that swing is highly dependent on the black hole spin, because where this light cylinder is, this light cylinder becomes closer and closer to the black hole as it spins up. And again, that's sort of, again, looking at the large scale jet, which we hope to see with higher sensitivity observations from the ground. Going then back to the high resolution case, looking at what we might be able to do with the Black Hole Explorer by putting a dish, a component of our VLBI network into space, we should be able to get higher and higher resolution and begin to probe closer and closer internally into this ring. And this, I think, is very interesting because while we see evolution in the polarization on the large scales, which is spin dependent, we also see polarization evolution on small scales, which is highly spin dependent as well. So basically, we found that as you go closer and closer to the event horizon, the polarization is approaching the sort of more universal value that's determined by the black hole spin. And you see this strong swing up of polarization just in a few gravitational radii from where the ESG is observing to basically the edge of this inner shadow feature or the projected image of the black hole. So basically, if just looking at this plot, which is looking at image radius from the center of the image outward, we in the AST are sort of observing roughly around 5 RG, which happens to correspond to this photon ring feature that the BEX hopes to resolve in much finer detail. But we're basically only getting a measurement of this beta 2 at this sort of range. We can see that if we were able to sort of increase our resolution and zoom in just over this few gravitational radii, our models predict that we should see a very strong swing in this polarization just from the strong, basically the effects of the strong gravitational fields on the underlying magnetic fields as we get closer and closer to the event horizon. And so this strong swing up, I think, is a unique prediction of the effect of the gravitational field of the black hole on the underlying magnetic fields, which are producing our polarization. And it's also very spin dependent. So exactly how fast it swings up is a probe of black hole spin as well. And so by measuring this swing, I think we will have another way to potentially connect our observations of polarization to measuring black hole spin. But it's also a way to test whether or not our magnetic field lines are extending all the way down to the horizon and therefore potentially extracting energy from the black hole, or whether they terminate at some larger radius. And so by using this higher resolution of BEX in conjunction with the high dynamic range of something like the next generation EHT, which we actually need as well in order to image the things that are closer and closer to the horizon, because things are getting dimmer and dimmer there as redshift increases. We should be able to potentially resolve this swing up in polarization and use it to learn more about the black hole space-time. So yeah, I think just reiterating the connection between the expanded ground-based EHT array, which will help improve our dynamic range, and the addition of a satellite element to our array, which will improve our resolution by a factor of 3, are both really essential pieces for connecting these polarized insights, which we're now obtaining at a single radius to both larger and smaller scales, and get a more holistic picture of how jets are launched. So yeah, that is my talk. Thank you so much again for inviting me. Just the takeaways, polarization is really the key for understanding near horizon astrophysics. It's telling us much more just from the addition of polarization than we could ever learn without it by just looking in total intensity. Our polarization images we obtain from the EHT are consistent with magnetically arrested accretion disks, so very strong magnetic field near the event horizon and an outward direction of electromagnetic energy flux. And yeah, in the future, both with ground and space-based VLBI, we should be able to begin to directly probe the black hole jet connection on multiple scales. Yeah, thank you again. I'm happy to take any questions.
Thank you, Andrew. Lovely. Let me see. There's a delay with the other YouTube channel and people if they're asking. Thank you for this lovely talk. Are there questions here from the people in the call?
Yeah, I can ask
Yes,
a question.
please go ahead,
Alejandro.
Walter.
Thank you, Andrew, for this very nice and interesting talk. I have a question regarding, well, of course, I'm a particle physicist, so whenever we have a new observable, then or some new phenomena, we can always ask what are the chances that we can do a test for new physics with this, right? And then when I think about polarization near the horizon of a black hole, then it comes to mind things like looking for CP violating effects, or when people have considered like you have a black hole and then you have a cloud of some pseudoscalar like an action in it and all that. So how what are the prospects for having this type of measurements? If at some point we can see any either time variation or any rotation in the polarization that we can say, well, this probably, if we look at the simulations, this probably doesn't come from just say standard model physics, but then we can measure some violation of CP, for example. Or if at some or if there is no hope, just due to I don't know the turbulent behavior of the plasma to actually ever be able to say we can see deviations here from what the theory predicts.
Yeah, I think that's a great question. It's definitely an area a lot of people are working on. So trying to understand, yeah, what sort of more exotic gravity theories, as well as things like axion clouds around black holes, how that would impact the images that we see, and the polarization as well. It's not something I'm an expert in, because I do think we still have a lot of work to just, even measure the black hole spin, which is, one of the big Kerr parameters, which we think sets the physics of the black hole that we basically have little handle on right now, for M87. But one thing that I think is exciting for potentially testing future sort of, yeah, how complete our picture of the Kerr black hole is for explaining the space-time in M87 is the fact that we're, I think, seeing more and more how there are different avenues to testing spin. And so I can imagine a case where we are able to collect all those observations in the future and see if they align on one answer, or if they're different, in which case that might be a hint that there's some new physics. So for example, this polarization, which again is my focus, so I talked about it, is one way of potentially measuring spin, but just by looking at the photon ring, which is the main reason that BEX is being designed, this sharp feature of extreme gravitational lensing, the shape and size of that ring relative to the rest of the emission is also a strong probe of spin, which is again something that Alejandro and Delilah and others on this call are expert in as well. And so I think by measuring, potentially, hopefully by understanding more and more of the theoretical uncertainties and all these different approaches, we can design different tests of black hole spin in the same object. And that, if they agree, that would be great. And if not, I think that might be a hint of new physics. So that's sort of the approach I take to it. But I think, yeah, there are also many people who are looking more directly at exactly what, yeah, sort of beyond GR physics might entail in terms of these images. Yeah.
Thank you.
Thank you. Are there any questions here from the call? I don't see one from YouTube.
I have a question.
Go ahead, Pablo.
Hi. Thank you, Andrew, for the talk. It was very nice. I have a couple questions. First, in one of the first slides, you showed these different methods of resolving data to get the polarization tick plots. I just a curiosity, like if you can tell us a bit more how these methods are different, and I guess the only ones that I've the ones that we usually see are the EHT imaging, right?
Yeah, I think that's a really great question. And like I said, I think it's one of the successes of the EHT that we've really spurred a lot of development in this data analysis problem of how to turn interferometric images into data, interferometric data into images. Basically, I think this is sort of a rough categorization, but I think three main classes of algorithms that we have are basically sort of the clean-based approaches. This is sort of the standard method, which goes back more than 50 years at this point. It's used for most interferometric imaging. And basically what that's doing is it's taking a dirty corrupted image in the image domain and trying to clean it up sort of by deconvolving the point spread function off of the image in the image domain. Then sort of the innovation when I entered the field and which we built EHT imaging around now almost 10 years ago is this regularized maximum likelihood approach, which basically is using a forward modeling gradient descent approach by sort of defining a forward model from your image to your data and basically just fitting it along with a sort of likelihood and a cost function, fitting an image to your data. And you can, in that, include a lot of different sort of flexible regularizing functions, which allow you to penalize or favor certain image features, as well as use very different data products beyond what would be allowed in clean. So one of the innovations that we developed was, being able to use calibration in variant terms that are insensitive to some of these more difficult to calibrate features of images. And then I think more recently, in the last few years, people have even taken the next step beyond that and are now developing more and more of these sort of Bayesian MCMC approaches, which are actually fitting thousands of parameters simultaneously along with their full uncertainties with posterior exploration. So this is, again, sort of beyond going even a similar approach to the idea of regular likelihood, but going even beyond that to now begin to explore the uncertainty of these images as well as the most likely value. So I think, but all these different classes of algorithms make different choices under the hood. They all use many different choices. And so I think, again, like the fact that we were able to test them all against each other and arrive at similar results, basically, it's those cases where we have the highest degree of confidence in the results that we obtain, which is exactly what we found in the first polarized images here.
Yeah, thank you. I have a lot of questions, but maybe someone else can. I don't want to take all the time.
Go ahead. We still have 3 minutes. Please go for it.
Okay. So about these beta 2 observable, I was wondering, maybe for M87, this is something that can be. I mean, it can be considered as, let's say, constant, but for more variable black holes like Sagittarius, then how can this observable be used effectively, like time average or something like that?
Yeah, so I mean, I think already, right, we're seeing that beta 2 is actually varying in M87. And I would say it's varying over the years that we have images from 2017 to 2021 at the moment. It's varying more than our theoretical models predicted. It's actually the opposite of sort of what Sagittarius star, what we're seeing in terms of the overall variability of Sagittarius star, where the models are varying more than the data. So I think the best case is that we get sort of more and more observations. We keep getting allowed to go back, and we can obtain an average value of this beta 2, as well as all the other black hole properties, as well as some measurements of their fluctuations. Because I think, we're already seeing epoch to epoch in M87 that we are seeing variability, and that I think is a prediction of the simulations and of just the timescales involved. But the precise level of variability is something that we still want to understand more, as well as measuring the mean value. So basically, I think the dynamic nature of the plasma around the black hole is, I think, evident in these snapshots we have so far, and hopefully by continuing to observe, we'll get a better and better handle on what the average value is.
Okay, thank you.
I think I have 2 minutes. Let me just ask a quick question for you, Andrew. What is your idea of time averaging? Is there like a clear notion how this should be done? For example, for an image, I can take, 10 images and then I average them. Am I allowed to do that for vectors, or when I'm thinking about polarization? For example, can I take these 3 vectors and then just take a simple average? Is there like a clear procedure how one should approach that for the variability? In some sense, let's say I give you this data that you have in this slide. Is it trivial, the average, or should I be careful about that, or what's your take on that?
Yeah, I mean, I think you should always be careful. I think, for example, like things with the degree of polarization we know tend to decrease as you average more. And so maybe then in that case, a simple average of the vectors is not giving you a reliable measurement of sort of the average magnitude. So you do have to be careful about things like that, especially for polarization, which is this intrinsically vector quantity. But I think for the direction, simple average is probably going to be a pretty good indication. But you should, I think more and more sophisticated approaches can't hurt. So
Okay.
Yeah.
Well, okay, wonderful. I think like people, if they have more questions, they can contact you. I lost my YouTube screen. I don't see anything else. But oh, yeah. Okay, there's a question there really quick, Andrew. Sorry. Is there a model for black holes elementary particles? I don't know how to address that question. I just saw it, and there's a delay, Andrew. I don't know if
Yeah, so I am not a particle physicist, so I'm not maybe the right person to answer this question. But I think, one of the amazing things about black holes is that we think that they should be entirely described in terms of just their mass and their spin. So in that sense, in terms of their gravitation, all effects at least, they are very simple and elementary particle-like. And I think it's one of sort of the key goals of this whole field of research to understand to what extent that is true and how we can actually probe the mass and spin. Given all the astrophysical uncertainty of the fact that we're not performing a clean experiment, we're observing a messy system millions of light years away, which has this complicated plasma orbiting around it. But yeah.
Great. Thank you, Andrew. Thank you, everyone, for attending to today's Law Physics webinar 199. So the next one, we are celebrating our 200th webinar, so stay tuned for it. And we are very happy, again, for having Andrew today, giving us this lovely webinar. So thank you, Andrew. Thank you, everyone, and see you next time.
Yeah, thanks again for having me.
Let's do. Thank you. Good. Wonderful. Wow, you have 38 views, Andrew, on YouTube, which is like twice or